todos. Entonces, hoy pues tenemos un coloquio especial de los Elmegreen y le doy la palabra a Silvia para que lo presente adecuadamente. Let's start the colloquium.
Buenos días, buenas tardes. Hoy tenemos la oportunidad de tener ante nosotros a Bruce Elmegreen. Es un distinguido astrónomo que nació en Milwaukee y estudió en Madison, Wisconsin, y obtuvo su doctorado en Princeton bajo la supervisión del doctor Archival Spitzer. Ha estado trabajó de joven en Harvard y luego se fue a la Universidad de Columbia y lleva ya muchísimos años en el Centro Thomas Watson Research Center, en el Centro Thomas Watson de Investigación de la IBM. Ahí ha estado trabajando en una serie de proyectos con IBM y con proyectos astronómicos. Su tema ha sido el gas interestelar, y le ha preocupado mucho la formación de estrellas en nebulosas gaseosas y la estructura a gran escala en las galaxias espirales. Se ha preocupado de las galaxias espirales, de las ondas de las ondas para formar las espirales, para las galaxias espirales. Ha estado trabajando recientemente en temas como lo que llaman las little things, que son las galaxias, un conjunto de 40 galaxias pequeñas, irregulares en el universo local, y ahora nos va a platicar también de formación de las partes de infrarrojo, de formación de estrellas en galaxias. Ha sido también presidente de la División de Medio Interestelar en la Unión Astronómica Internacional, ha contribuido significativamente en esas labores y ahora tenemos el gusto de tenerlo aquí. Please, Bruce, go ahead.
Thank you, Sylvia. Thank you, Jesus. I will share my screen.
Mm-hmm. Great.
Can you see that okay?
Yes.
Good.
Yes.
So it's a real pleasure to be with you in this remote way, but nevertheless, to see many faces I recognize. So thank you for this opportunity. I'm going to talk about a problem that's interested me, I think, since the beginning of my career, at least since the late 70s, and that is the connection between star formation and spiral arms in galaxies. It's an old problem. It's an unsolved problem. What are spiral arms doing for star formation? And I think the answer is now quite evident based on really archival data that we've had for 10 years, but not really recognized. And this has to do with the 8 micron cores that are present in Spitzer data. So this is a talk combining these three things. You know the story, really, it goes back a long time. Ever since blue photographic images were available, astronomers like Bada realized that there were different colors to galaxies, that the blue, namely the young star-forming regions, tended to be in the spiral arms. And he had a very graphic expression for this, strung out like pearls. And here I've shown 3 different kinds of spirals, flocculent spirals and the grand design on the right, 2 main arms and multiple arm galaxies, which all show these blue or bright star-forming regions. But the question is, what's happening here? In the 60s, we began to understand that there were stellar density waves, which are gravitational instabilities in the stars, and that they would have a certain co-rotation radius, and inside that, the gas and stars would move through the waves faster than the waves. And as a result, on the inner part of the spiral arms would be a shock in the gas, and that's what the dust lanes are, and you can see them very clearly here. But then there was a story that was really built up for how you would get these bluish star-forming regions or H2 regions downstream. And yet very little evidence for that because of all the irregularities. There's extinction that's blotchy. So you can't really see what's happening. You can't see what's happening in the dust lanes. There are H2 regions which are equally blotchy, and the OB associations are irregular. They're spread out quite quickly after they form. So you don't have a good picture of what this process is, what density waves are really doing. Well, a couple of years ago, working with Yuri Evermov from the Soviet Union originally, and then Russia, known him for a long time. He passed away a couple of years ago. He was interested in a particular galaxy, NGC 6946, because of large shells and other things. And so he got me looking at Spitzer IRAC images. And I recognized in other images, in particular this one, M100, that the spiral arms and all of the structures, including the shells, were just dotted with these emission peaks, which are mostly at 8 micron. And you can see them here. Sometimes they're very regular. Sometimes even in long spiral arms, they're present. But everywhere you look, there are these little dots. So Debbie did an unsharp mask in a way dividing the 8 micron image by the 24 micron Spitzer image. 24 micron has a larger angular resolution, so this is like an unsharp mask. It's not exactly. But that was enough to remove the average radial profile of the galaxy, which is the exponential disk, and also a lot of the local structure. And here you can see these dots very well. And most of these have no obvious optical counterpart. Look at these 5 or 6 dots here. What do you see optically? Hardly anything. Or these 1, 2, 3, 4, 5, virtually nothing. Now, if you look really carefully, you might be able to see some of them here and here. But mostly the overall perception of a regular pattern of a narrow spiral arm piece or gaseous filament with a regular pattern is not at all apparent. Even in this main southern arm, which has got lots of strong star formation, it's got this dusk that obscures everything, and the little blue dots are quite irregular. But in the infrared, you see it to be regular after all. So we define 27 filaments, and in those filaments, 147 clumps to measure the properties of the clumps in the filaments. There are about 400 total in this galaxy, and found that there was an average separation along the spiral arms of about 410 parsecs. So here's a histogram of the neighbor separation. And here's a histogram of the relative separation. That's the separation between the pair on the left and the pair on the right. That difference, if that difference is 0, then they have the same, all those 3 in a row, the same separation. So if that difference is 0, which tends to be, that's where the peak is in this histogram, that says that the condensations are regularly spaced. If they're regularly spaced with a gap in them, then you see the secondary peak. So there's a great regularity to many of these little clumps that are in the spiral arms and other filamentary pieces. Also, the ratio of the clump separation to diameter is about 3. Well, these numbers, this regularity and the spacing, is reminiscent of what we've known for a long time about gravitational instabilities in filaments, in particular filaments that are close to their critical line density, where they collapse in the perpendicular direction. Filaments are always unstable to collapsing in the parallel direction. There's no critical value of line density for that. But if line density is very low, then it takes a long time to do that. Also, the simultaneous appearance of many clumps, triplets or quadruple clumps all along a filament length, suggests that that filament all formed at about the same time. Or else clumps would come and go. They wouldn't necessarily be all at the same phase of dense infrared clump. So now here we have a picture where these large scale flows, in particular around a spiral density wave or maybe a large filament, that is a shell with a shell at the edge, produces filaments which collapse gravitationally, produce stars. Very similar to what we see locally on the 1,000th the scale. In the early universe, as you know, gravitational instabilities look much different. At high redshift, galaxies are gas-rich, highly turbulent as a result of a high accretion rate and interactions with other galaxies. Gravitational instabilities there make big clumps, even in the stars, but particularly in the gas and in the star formation. But today, accretion rates are much lower. The gas is less turbulent by a factor of 5, maybe in velocity dispersion. And a long history of relatively slow star formation following that lower accretion rate has built up a cool stellar disk with a low gas fraction. We still see in today's galaxies remnants of that original hot, thick stellar disk. That's the old thick disk in today's galaxies. But mostly what we see in optical light is the cool stellar disk and the evidence for star formation. And in that cool stellar disk, gravity is still important, but it makes spiral arms, which just grow in time at a rate in proportion to the rotation rate. And the gas also has gravitational instabilities, which clump up wherever the gas density is high. And that tends to be in spiral arms in the cases where there are spiral arms, or along shells, the edges of shells, and so on. So this next study is for 15 nearby spiral galaxies, such as NGC 628. Here you see the Spitzer image, and here is on the left that type of unsharp mask we did before, dividing the 8 micron by the 24 micron image. And on the right is the 8 divided by a blurred version of the 8 micron, where that blurring is 3 pixels. And that's a much better way to look at it in these cases. We remove the exponential disk, we remove all the local structure, remove some of the irregularities, and we see all the little dots very clearly. So here is 628 in the 8 micron, and here is the unsharp mask image of exactly the same thing to the same scale. Oh, this is actually a color, it's a combination of the 4 IREC bands. So if we compare these two, if you look at any dot, you'll see it in the combined IREC color, but it really helps to bring out the pervasiveness of this dotted structure with the unsharp mask image. Here's another galaxy, 3184. If you look closely here, you see it's just full of dots. By the way, the blue dots are stars, and the red color is the gas and star formation regions in the galaxy, which is dominated by, as I'll show you in a minute, highly extincted photospheres plus PAH emission. So the foreground stars are very clear in these images. There's that unsharp mask image of the same galaxy. You can see again, dot for dot. 3351, that's got that really cool ring in the center with dots in the ring, but also dots everywhere. Also, this is more of a flocculent type galaxy. 4254, multiple arm type, and so on. So here's a histogram of the apparent magnitudes. And we sort of arbitrarily take a apparent magnitude cutoff of about 16 to include most of the fully selected clumps. We're probably missing some around that magnitude limit. So all the light blue or cyan color, we're going to ignore it in what is what's coming up. The heavier blue, the darker blue, I'll show you some results from those. And the red histograms are for the two cases where there are strong granidine spiral arms, 1566 and 5194. And the clumps in those arms, which are the red histograms, are a bit brighter than the clumps elsewhere in those galaxies. But it's kind of remarkable. All of these galaxies look about the same. They're all equally clumpy. And from these histograms, you can see they all have about the same number of clumps within a factor of 2 or 3, even though the galaxies are at very different distances. So we know we're missing the smaller clumps in the more distant galaxies. The same clumps we would see in local galaxies, we would be missing in more distant galaxies, and yet all the galaxies give us the same visual impression. So why is that? So that's primarily a selection effect, I think, just because these are from the archive, they are from surveys, particularly the SING survey and others. They're for local galaxies. And so they're chosen to all have about the same angular size in the sky. And on the right here is a plot of the average separation between the 8-micron cores, 1/square root of their density in kiloparsecs, and the radius at 25th optical magnitude in kiloparsec. And you see there's a correlation. So the bigger galaxies have a bigger separation. That tells you right away we're missing some of the small objects. These bigger galaxies are at greater distances because they're all chosen to have about the same size. So we're missing the smaller ones because we can't see them. They're too faint at these larger distances. And that all works out in a self-similar way simply because the luminosity function of star-forming regions with clusters or OB associations tends to be about luminosity to the power -2. So that means the total number of cores exceeding a minimum fixed luminosity, maybe what do you think is the minimum cluster size or the minimum size? Maybe it's 10 solar luminosities, whatever you think that is. The number exceeding that just depends, now you want to integrate over this distribution function, just depends on the ratio of the largest luminosity to the smallest. Similarly, the total number exceeding a minimum observed luminosity, that's my observational cutoff, where it does matter that some galaxies are further away than others. The number exceeding an observed minimum is that same ratio of the maximum luminosity, which I always see, to that observed minimum. So if we have fixed 8-micron core properties, that means a fixed minimum luminosity and a fixed spatial density, then the total number I see, because of that fixed density, total number present, actually, not those that I see, the total number present scales with the galaxy size, R25 squared. And because of this ratio, therefore, the maximum luminosity scales with R25 squared, the area or the total number. That's the size of sample effect. The maximum luminosity scales with the size of the sample, which is the total number, which is proportional to the area of the galaxy. So when all the galaxies in the sample have about the same angular size, the area and the maximum size both scale with distance squared. Similarly, for apparent magnitude, for a constant limiting apparent magnitude, the observed minimum luminosity scales with the distance squared too. That's just from the luminosity, from the flux being 1 / distance squared. So the number that I observe, which is the ratio of the maximum luminosity to the minimum observed luminosity, goes as the distance squared over distance squared, which is constant. So this applies to many features that you see in galaxies. Galaxies tend to look self-similar, even those that are far away and those that are nearby, primarily because of this universal scaling of luminosities of star-forming regions. That also applies to H2 regions. Here's the color diagram for Spitzer colors. There's some 6,000 cores in all of these 15 galaxies, so they're plotted here. We've excluded the cores that are those blue dots. Those are the ones where the 5.8 minus 8 is less than about 0.6. Those are known to be, that's your typical Vega type magnitude of a photosphere. And the average 3.6 minus 4.5 here is about 0.21 magnitudes. It would be 0 for a Vega star photosphere. So that difference of a couple tenths of a magnitude tells you the extinction. And then in fact corresponds to a rather large extinction, some 15 magnitudes, because these colors are so close, well, they're near infrared, but they're so far in the infrared, the extinction is not so important. So a little bit of a excess above 0 corresponds to quite a bit of extinction. So these objects are typically behind 15 magnitudes of extinction. There are some 300 solar masses per square parsec of gas. And also the 5.8 minus 8 being around 1.5 to 2 tells you you've got a lot of 8-micron emission, which is mostly PAH emission. So these are highly extincted young star-forming regions. Now I can extrapolate the total IRAC luminosity, that's all 4 bands, to the bolometric luminosity for a young stellar population. And then to mass, again for a young population. And now I can derive the summed mass of all the cores that I see in each galaxy. And I know I don't see some, again, because of this L-2 relation. The missing number is about proportional to the number of logarithmic intervals that I'm missing. So I can correct upward the sum mass by maybe a factor of 2. But nevertheless, right here, I plot it to that summed mass. And you see that the star formation rate measured in the usual way, maybe it's H alpha, maybe it's 24 micron and UV. The star formation rate total in the galaxy is scaling directly with the sum of the core mass, and the ratio of these two gives you the lifetime of these cores, which is between 0.1 and 1 million years if we just take the cores we see, or I double that to account for the missing cores. So if these are truly young regions, million years, 500,000 years, then we are seeing all of the young regions, and we have a new way to measure the star formation rate. And it's giving the same rate as H alpha would give, and also the same rate as the FUV and the 24 micron would give. And all of these measures of rate are sampling a different epoch in the lifetime of a young star forming region. These cores are showing you their birth. And H alpha is showing you 3 million years to 10 million years. FUV and 24 micron is showing you general radiation and heating from a young stellar population, including B stars, and the FUV goes out to 100 million years or so. So we think we're seeing the youngest phase, and that we're measuring the same star formation rate as we get in other measures just tells you we're seeing part of that pipeline. So now let's go back to 628. Here's a nice optical image, ground-based optical image, to show you the contrast. Just with Spitzer, already you see a lot because the Spitzer IRAC images are showing you primarily the dust, which is the gas. You don't see all of this haze of blue stars, and you don't see the H2 regions. Here's the unsharp masked image, and here it is compared to optical. So now you could really understand what we were missing in these decades since Bill Roberts wrote his 1969 paper about what spiral density waves could be doing. We really couldn't see it. And now I think it's pretty clear. One for one, you can see these dots match up. But certainly the unsharp mask image at 8 microns shows them better. And it shows a clear outer edge also. What about the Milky Way? Well, we've known the Milky Way has spiral arms from H1 studies back in the early 50s, a couple of years after 21 centimeter emission was seen. And in this paper, I show this particular one. This is where the main spiral arms in the solar neighborhood were first named: the Orion arm, the Perseus arm, and the Sagittarius arm. And the one out here is the Perseus arm. The one that shoots off in this direction they called the Orion arm, passing through the sun. This is Perseus Orion arm, and then the Sagittarius arm, which was seen in the original studies with Bod and Code and others in this region, seen as the blue spiral arms, not seen in this particular map of H1. Well, a more modern version of the H1 shows it looking like this. This is the outer part of the Milky Way, and it's clumpy. Smoothing length for this map is about 0.5 kiloparsec, and you'll remember that was the separation between the clumps in M100. So we're not going to see that kind of structure here, but there's also a real a knotted structure along these main spiral arms, very much the same as what we see in these other galaxies. This is the inner part of the Milky Way, now seen mostly in CO. You see it has a clumpy structure. That's a Sagittarius arm, a Carina arm in through here. So let's look at some of the Starframe regions. This clump in H1 corresponds to W345 in the Perseus arm. And there it is in the sky. The total extent is about 150 parsecs. It's very young in this region, W3. This is a bit older, an expanded H2 region, another expansion, knots or bright rims right here with stars, young stars in them. So this whole region may be 5 to 10 million years old, but with this region maybe 1 to 3 million years old. Also in the Perseus Arm, NGC 7538, another enormous region of star formation in the Perseus Arm, similar structures, shells, condensations, embedded sources. Seen in the sky at in CO, they have a separation that's 400 or 500 parsecs. And they overlap somewhat because they're at a little bit different distances. But these are the main star-forming regions in this part of the Perseus spiral arm, and they're highly clumped. If we look in the fourth quadrant, NGC 3603, another major region of star formation, and it's optically shown here, but it's just a piece of that molecular cloud, which is one of many molecular clouds in this concentration of molecular clouds, which represent the densest parts of this giant H1 cloud. This H1 cloud contains about 10 to the 7th solar masses, and so does this one, and so does this one. These are all at positive velocities, so they're inside the solar circle. And each one of these giant H1 clouds corresponds to a cluster or clumpiness of little molecular clouds. The molecular clouds here are 10 to the 5th solar masses, the H1 cloud 100 times bigger. So these are just the dense regions of much larger structures in the Carina arm. Here's another one. The separation between these two is not that different from what we saw in M100, 0.6 kpc here, would be 0.4 in M100. Here's the negative velocities. So these would be outside the solar circle. They're a little bit closer as well. Another big H1 concentration. This is another enormous famous region of star formation, Eta Carina. It's just a piece of that molecular cloud, which is part of this condensation. And here again, you see a separation of about 0.5 kiloparsec. So our galaxy has them too. What's happening? Here's a little schematic I drew in an old paper when I first started thinking about this. We knew at that time, and this was 10 years after Roberts, that gas would come into a spiral arm and it would shock, which means it would bend sideways and come to a little bit denser, at which point gravity would operate. And I had been working on triggered star formation then for a couple of years. So I thought, well, maybe this extra density can give an instability. What would happen then? Well, it would be self-defining. It would be an isolated, now independent object. It would break off and the dust lane would form again because there's a reforming shock. The density wave lasts longer than this. And this would form its stars and break apart and scatter around by pressures and do that again and again with other generations downstream. Well, since then, there have been very nice simulations showing this basic process. This was Kim and Ostreicher were the first to redo this problem in numerical simulations. Here's from their 2007 paper. It's just a shearing sheet, which is a 2D layer, not a whole part of a galaxy, which is shearing, initialized with perturbations. And those perturbations would shear out and stretch, but also they would be dense. They would grow sideways because of gravity, and then they would collapse into little clumps. These were very early days. This shows more the same process now in an annulus around a galaxy with rotation present. And in this case, in Dobbs' paper, without self-gravity, there'd be little condensations in the arms, but they would not be regular. With gravity, they'd be regular. And in both cases, these condensations are from a coagulation of clouds, because after all, what's in the inter-arm medium is just a bunch of little clouds. Most of the mass is in diffuse clouds here, or maybe molecular clouds, and they collide together in a haphazard fashion in general, giving a random clumpy structure. But when gravity is present, that clumpy structure becomes regular because these pieces see each other. Again, this simulation was just turned on. It's not necessarily a steady state, so you see a regular structure that's all forming at about the same time. In the case of a simulation, it's just turned on because you don't have that much time in a computer to run it around and around many times. Renaud did this study. Again, this is a young instability. It hasn't gone for very much time, and the spiral arms form first very quickly in the gas. This is to simulate the Milky Way with very high resolution. Some of the spiral arm structures look like Kelvin-Helmholtz or shear type instabilities, maybe wiggle type instabilities, but others are really growing clumpy structures from gravity that form in about 10 million years. So the Bonnell and Dobbs paper from 2013 gives us a clock. It tells us what is the time scale, because they watch gas come into the spiral arms and shock and come out again. And here are 4 frames at these different time scales: 17.9, 25, well, actually 0, they can start counting, 17.9, 25, 46. So a typical time scale for the shock presence is about 30 million years. It's a large fraction of the total time going from arm to arm, which could be maybe 150 million years. It's such a large fraction because the density is high in the arm, in this shock front. So the continuity equation tells you that the flow through speed has to be low wherever the density is high. So the gas is in this shock front for quite a while, which is something that would be hard to get without these simulations and without direct measurement of the density in the shock fronts or in the dust lanes. These are not molecular bright regions. So Debbie actually worked on this for her thesis, trying to get densities in these dust lanes, deriving values of maybe 5 or 10 per cubic centimeter, modest densities, sort of diffuse cloud densities. But without that measurement, you don't know how long the gas has to stay inside a dust lane in order to become gravitationally unstable. And if it comes out too quickly, it's not going to condense in the dust lane. It may do something later. Maybe there's a different picture. Maybe it's a picture where clouds come in and shock and then plow right through and star formation happens in those clouds. That's a model. But without knowing the density or knowing the timescales, we can't really say if gravity has enough time to work. So here's a measurement now just based on the simulation. So it's something less than 30 million years. Now we have all we need to know to get pretty far. So if the clumps are filament instabilities and the regularity and the 3-to-1 spacing suggests that, then that tells us what the ratio is of the mass per unit length divided by the density. That's what gives you the length scale. The critical unstable length just depends on the velocity dispersion. And that, I mean, the critical unstable line density just depends on the velocity dispersion, sigma, and the gravity constant. So this ratio of mu over density, square root, is the length scale. So now we know the ratio of mu over density because we have a separation length. If the growth time is less than 30 million years, that gives us the density. So it has to be greater than around 5, which is about what Debbie mentioned in her thesis in 1980 or so. Combining these now gives the mass per unit length, some 1,500 solar masses per parsec. And therefore, if it's critical, around a couple kilometers per second. So the gas coming in cools. It is like a diffuse cloud. It cools from a velocity dispersion of maybe 5, 10 kilometers per second, down to just a few kilometers per second, which is why it's so thin. And then the mass per unit length times the separation gives you a typical mass of gas connected with one of these clumps, several times 10 to the 5th. And you'll recognize that number as a typical GMC type mass with peripheral H1, not the 10 to the 7th major complex surrounding this, but what's directly associated with these clumps. In fact, that mass compares well to the star formation mass. If we take the summed mass of 10 to the 5th or 10 to the 6th and consider that there's several hundred of these clumps per galaxy, that gives you several thousand solar masses per star forming clump. And that's your typical efficiency of a few percent. So the separation and the time scale, which comes from the simulation, separation directly measured, gives an unstable mass, and that agrees with the IRAC mass. So now let's take a pause and face on galaxies and do the same thing for edge on galaxies. In the Spitzer archive, there are 3 good case edge on galaxies where we can really see a lot of 8 micron clumps. And those are these 3 cases. So here on the left is the 8 micron unsharp mask image of 891. Look how intensely straight that is and thin. And here it is with a blue dot, a measured blue dot at each core. This is how we find them. It's actually optical. You can't use it's extractor or some automatic routine because the structure is too irregular. We find them optically and we put a little blue dot there and then find the ones that are left over. Zero in on those with IRAF, measure their position, put a little blue dot there until there aren't any left over. Then we look at the color diagram and take away those that are stars, like this one down here, which has the wrong color, and so on. So that's how we find them. Well, here they are for 891. Here it is now with an optical image and divided into two parts. So the lower part here, the southern part is the top 3 bins, optical 8 micron, and all of the 8 micron sources we've identified as red circles where you can see inside them. And then the northern part here, optical 8 micron and the 8 micron identified sources. And you can see in some cases, an 8 micron source will have an 8 micron feature that's visible in the optical image like these. But mostly there's nothing in there. Now you're looking at an edge-on galaxy, so there's even more extinction. Sometimes you see them, sometimes you don't. Mostly not. So that tells you right away that for edge-on galaxies, you really do not see the star-forming regions. There's just too much extinction. This is 3628 with that beautiful little, in this case, it's a different galaxy. Then I showed you the oval core. That was a different galaxy before. This is a now edge-on, beautiful little core. This is showing a thickening of the disk over here because this is an interacting galaxy. Here it is, optically, a lot of distributed stars that have just been scattered from the outer part with a wobbly kind of flop in the outer part of the gas disk here. But at 8 microns, it's really very razor thin. The inner disk is hardly flared or warped at all. You only see a flare on this side corresponding to this flaring of the gaseous disk. And a little bit of thickening correspond to the thickening here. Stellar disks are very stable. If you perturb them perpendicularly, they restore themselves, wrap around, and eventually become flat again. A little thicker, but flat. And here's 5052. And it's optical image with 2 very brilliant foreground stars that are actually in the galaxy here, but they're not extincted, so they look blue. There they are. They're part of these, and these red things here are foreground stars that are not part of this galaxy. Well, here's a distribution of perpendicular distance from the midplane. For 891, this tells you the thickness of the galaxy. It's about 100 parsecs. For 3628, it's 300 or 400 parsecs, because this is that thickened disk. It's an interacting galaxy. And 5052 back to 100 parsecs or a little bit more. And this is the thickness, the scale height. Now, you realize you rarely measure the scale height in another galaxy. It's hard to measure even in our own galaxy. We do it with CO. You can do it a little bit with H1. You can hardly do it with stars, but you can now with Gaia. But in other galaxies, certainly face on, you don't get thicknesses. Unless I did this for the LMC, you can look at the Fourier transform and see where there's a kink. Francoise Combs did that for M33, but otherwise, you don't resolve the thickness. And so even in the Fourier transform, you don't see that kink in the slope of the power spectrum of the Fourier transform. But generally for face-on galaxies, you don't see the height or the thickness. Here we have 3 edge-on galaxies, and we're actually looking at star formation in them, so we can get the height of the star-forming layer. Here it is for 891, and there's a very slow thickening of the star-forming layer. 5052 has a decrease, but that's got a slight tilt to it. A tilt would give you a decrease, because when you're looking along the center, you see the front and back side sticking up above the center. So it gives you a slight decrease. 3628 has a slight steadiness or positive, but you could see in the lower right panel, that's just the warped position. So here the warp is the negative part, and the non-warped is the positive part. So you see the warp is very thick. And in the non-warped part, it's pretty much flat thickness. So generally, you conclude that the star-forming disks have a very slow rise here and here. Perhaps they're agitated by an interaction. Perhaps you don't quite see it because of a slight tilt. Also in the Milky Way, now from CO, this is in Hare and Dame's review, the inner part is pretty flat. This is the thickness, molecular full width half maximum in parsecs, some 100 parsec full width half max thickness, with a flare starting at about the solar radius. This flare is inferred for other galaxies as well, but mostly it's in the optical bright part of the galaxy. It's fairly flat or very slowly rising. Now that's an incredibly important clue to what's happening, because look what it says about the Kennicott-Schmidt relation with this 1.4, 1.5 slope for total gas. Now that the explanation of that becomes absolutely trivial. Nothing to do with feedback. It's just the general tendency for a galaxy to regulate itself by large-scale instabilities, trying to keep that turmeric Q about constant through spirals or through other instabilities. Because when Q is constant, then the velocity dispersion, which takes whatever value it has to maintain Q of constant, just depends on the ratio of the gas column density or some combination of the gas in stars, which I just write as gas here, divided by the epicyclic frequency. So that gets its velocity dispersion by multiple continuous gravity actions, either spirals or condensations, inside a generally exponential disk. The thickness just comes from the dispersion and from the mass column density in the disk, so that gives us the density. And the star formation rate just comes again from that gas column density, which is a measure of how much gas there is per unit area, multiplied by the rate at which gravity operates on that gas, which is the square root of density. Now you know everything. Here is a blue plot of just this star formation rate for different rotation curves, a rising rotation curve or a flat rotation curve, it doesn't matter. The slope in the main disk is about 1.5. One is what you see for pure molecules, say CO, the CO-Kennicott-Schmidt relation, because of the selection effect that you're just choosing CO, where the density is always about the same, because that's the excitation density. And so the time scale is always about the same. And so you just get the rate proportional to the amount of CO, always with the same intrinsic time scale. If you take the total gas, you get this slope of 1.5, simply because the thickness is about constant. And so the square root of density is about the same as the square root of column density. Also, if we look at perpendicular disks, we can see structures. Maybe they are shingles. They're present in our own galaxy. They've been known for several decades. You can see irregular structures. Maybe you think these are shells, stuff tossed out and forming in condensations in shells. These are little shingles. 3628 has all of this splatter of stuff from the interaction. It's got these, what are these shingles? Actually, the separation, if you deproject this little arc, the separation between the dots is around 400 parsecs. So these could be spiral arms. 5052 could have shingles as well. So just to summarize, for the edge-on case, we see hundreds of these 8-micron cores in each of the 3 galaxies. And there are other edge-on galaxies in Spitzer which show a more irregular structure. They don't show so many 8-micron cores. So we chose these to get a good measure of statistics. There aren't that many edge-on galaxies in the Spitzer archive. So if we take the average extinction for the face-on galaxies as about 15, which I told you before, the extinction measured from the color diagram in the edge-on cases is another 8 to 10 magnitudes. So that's the foreground extinction, corresponding to some 100 solar masses per square parsec foreground with the, if we assume the standard 15 or so magnitudes, 300 solar masses per square parsec local. And that corresponds to about a 1 atom per cubic centimeter, typical ISM type densities. The average young stellar mass in each of these edge-on cases is about 10 to the 4th, a little more than what we get for face-on, because there's more extinction, we're not seeing as many. The ratio of the core to star formation rate in these, I didn't show you for edge-on cases, but it's about the same, 1 to 2 million years. So we're seeing, again, the earliest stages of most star formation and missing some of the smaller ones for this highly extincted edge-on case. Half thicknesses make sense. For 891, it's about the same as the Milky Way. Same for 5052. For 3628, it's much thicker, but there's a flare from the interaction. There are loops and also condensations in these, what are likely supershells or blowout edges. And most of these cores were not recognized before. And then in general, it looks like most star formation in today's disk galaxies occurs by gravitational collapse in filaments. And these filaments can range over 4 orders of magnitude in size, from tiny little local solar neighborhood filaments to giant spiral arm filaments, with this, what's likely the same physical process. Spiral arms and spurs are local condensations, pressures, collect gas into shock fronts, or collapses by self-gravity. This is a property of our cool star-dominated disk, which the main influence of gravity is to drive stellar spiral arms, and then the gas follows that, shocking into kiloparsec-sized dust lanes, or perhaps pure feedback, which tends to operate very locally, can make bright rims or make shells, which produce similar kinds of condensations and further star formation. The perpendicular thicknesses of galaxy disks rise with radius a little bit, but much slower than the exponential of the column density. So that means the density is mostly following the column density. And so the square root of density, which is the rate of collapse, mostly follows the square root of column density. And there you get that extra 0.5 power in the Kennicutt-Schmidt relation. Okay, so that's what I have to say today about spiral arms. And I could stop sharing, leave this up for some questions. Thank you.
Thank you, Bruce. Really interesting talk. Well, the preguntas. Okay, let's start. Aida?
Hey, Bruce, how are you?
Aida. Yeah.
So you showed for the edge-on that the clumps, some are in the middle plane, some are, 100 parsecs from the middle plane. And some people age date H2 regions based on morphology. And so I would expect the clumps that are 100 parsecs from the middle plane to become ring-shaped H2 regions very fast just because they burst into the open space. So is it possible to have an H2 region that looks like a ring that's just as young as one that looks, concentrated, where the gas is on top of the stars, but it's just that the one where the gas is on top of the stars is in the middle plane?
Yeah, that's a very good question. There is a depth effect which we tend to not see in face-on galaxies if we just look at the H2 regions. There would be this effect that you mentioned. A blowout or expansion is easier at lower density, which would be the front and the back part of the galaxy. Even if you're surrounded by a perfect sphere, there'd be some rim brightening. So you'd see a little bit of a shell there. But yes, you raise a good point. Classifications may have in mind that all the H2 regions are midplane and they all have similar environments, but that's certainly not true. Not only are they not midplane, but they vary in their position relative to the concentrations of gas in spiral arms and spurs. If they're all born in filaments, then you would expect more of a bipolar shape, which does occur for some very young regions and does occur for H2 region. I showed you W345. There's a general bipolar shape there as well. So that would be a predicted morphology of H2 regions that comes when most star formation is in filaments. If you look too late, you may not see it because that part of the filament blocking may be eaten away by then. So there is a lot to learn about predicted morphologies of H2 regions, given the filamentary nature and given the real 3D structure and the variation in local density.
Thank you. I have another question, but I'll wait. Maybe somebody else has something to.
You can go ahead, Aida.
Okay. Did you see any difference between the flocculent and the grand design? No. Okay.
No, not really. The regular spacing occurred only in the grand design and multiple arm, where you had the long arms. That's sort of what you would expect. But in terms of tracing the star formation rate or numbers or properties, no difference. We knew all along that the Kennicott-Schmidt relation was the same, whether you're in a flocculent or a grand design. So you knew all along there was the grand designs did not trigger a lot of excess star formation. They did not lie off some mean Kennicott-Schmidt relation. So in terms of efficiency, it's all about the same. And the properties bear that out. There's not that much difference.
Thank you. Good to see you.
Good to see you. Yeah.
Thanks. Additional questions? ¿Preguntas adicionales?
A ver, Joel tenía una pregunta. Luis Aguilar quería preguntar.
Pues no veo la mano levantada, pero ok.
Y no sé si
Luis.
Pepe también.
And Michael Richard.
Michael.
Yeah, hi. I was just wondering about bars. Hello?
Yeah, good. I have not included many bars. There aren't that many in the Spitzer archive. That would be interesting. I showed you some like ILR rings. There were some one or two barred cases in the 15 galaxies, yes. They pretty much show the structure you would expect without much a clumpy structure between the ring at the end of the bar and something in the center. Same kind of spiral arm structure that looks the same as non-barred galaxies, and then the little ellipse in the center. So it's pretty much what you would expect, not much hidden where you don't see much star formation. But in terms of the properties of the clumps, not much different.
Okay, thank you.
Excellent. Ok. Solo para confirmar. Joel, ¿tiene pregunta?
No, not from my side.
Okay.
Vladimir levantó la mano.
Vladimir
Okay. Sí, antes de irme a Vladimir, porque mencionaron que Luis también, Luis Aguilar. ¿Tiene preguntas? Ok. Go ahead, Vladimir.
Okay, thank you, Bruce, for your nice talk. As far as I understand, the formation of this course, for the formation of this course, is very important to have the spiral arms. So what about irregular galaxies where we don't have these spiral arms? What about the star formation in this case?
Yeah, good. So part of the answer has to do with the difference between flocculent and grand design or multiple arm. Flocculent still showed these with a few because it makes spirals nevertheless. But I have been looking at the little things galaxies, the local irregularities. It also has these 8-micron cores. In no particular regularity, I do not see 3 in a row. It's also irregular. I don't know now about the statistics. I haven't looked at that yet, but these all tend to be fairly close. These are local dwarfs, tend to be in the local group. And the absolute magnitudes are dimmer. So we're seeing dimmer regions. They would correspond to lower mass clusters, which we know tend to populate these dwarf galaxies. So it looks like the same story and the same scaling relation to now be for everything dimmer, but without the regularity. And if that means there are no long filaments, I don't know what that means for what gives the gas its condensation. What converts gas from warm diffuse to cool diffuse to molecular? That's a big mystery in dwarfs because we don't really see the molecules very easily. The extinction is so low, there's a lot of UV. That conversion seems to be difficult. The efficiency, you know, the gas consumption time is 100 gigayears or so instead of 2 for spirals, for the molecules. So things are different, and maybe we can get a handle on that. But just from the locations of the dots, I don't see any irregularity. It looks just as irregular as the star formation.
Okay, thank you.
Okay. Pepe?
Hi, Bruce.
Hi, Pepe. Good to see you.
Yeah, good to see you too. I was late for your talk, so I don't know if you said anything about the masses of the galaxies. Do you see any difference between, you know, big masses and more modest masses in the galaxies? Do you see any differences?
Yeah, that's a good question. I did mention that. I'll give a brief summary. These are from the Spitzer archive, so they tend to have been chosen already to have about the same angular size, the Singh survey and other surveys. So the more massive galaxies are further away. And yet all of the relative properties, the visual appearance looks about the same. The histograms of apparent magnitude look about the same. So it's telling you there's a selection effect. So the most massive or the brightest of these is scaling with galaxy area. That's a size of sample effect. The dimmest is also scaling with distance. And we tend to end up with about the same number just because of the way the star forming luminosity function, L to minus 2, corresponds to the flux luminosity function distance to the minus 2. So we end up with about the same numbers of clumps. So bigger galaxies have bigger clumps, but also the same smaller clumps. It all looks like it's part of the same universal power law, luminosity to minus 2 or mass to minus 2 for the individual features. And you're seeing mostly the size of sample effect.
Okay, thanks.
Silvia?
Okay, maybe you mentioned it, but I'm still concerned. Have you found any relationship between the 8 micron dots to the optical H2 regions? I know there are different epochs. I mean, they represent different stages of star formation, but can we find any combination or any probability or anything that will tell us that there's an effect within each other?
Yeah, that's a really good question. I think it was 2014 or something. I did a study like this with Debbie and with Johan Nappen, who brought in his really good deep H2 region observations. We did it for 3 or 4 galaxies. Only found a few embedded sources. We're disappointed then. We did not see what we see now. And that was also Spitzer. But we first thought that these were optically invisible, but then Johan Nappen did see that many of these had H2 regions, little specks of H2 regions sometimes. The current data does not show the same depth of H alpha as in the Nappen data, where he would have 500, 1,000 H2 regions, even little ones. So my guess is that many of these, which look indistinct optically, will have slight H alpha, but they are still somewhat embedded. The H alpha should still be extincted. And you may be seeing around the edges this sort of bipolar H alpha that I would expect from filamentary regions. The physical scales that we can resolve with Spitzer 2 arc seconds is 20, 30, 40 parsecs. So we know it's happening. You know, that's a whole OB association or a couple of clusters. We know there's a lot of substructure. There could very well be H2 regions with 5, 10 magnitudes, and the average is about 10 magnitudes around that. A lot of extinction. Paschen alpha, maybe in the infrared H2 region, you should see something. You should see, at 1 million years old, there should be ionization there. I do not know right now.
Thank you.
Thanks. Chucho?
Hi, Bruce. Thanks a lot. Very good. Very nice talk. I have a dynamical question. I mean, I was surprised to see, you know, how fast these structures get very thin again. And I would expect that if there is a mechanism I mean, what the mechanism would be to allow that. And it's a mechanism that precludes them also to go into the center. Can you comment on that?
Right, so by thin again, you must mean from one dust lane to the next one downstream.
And also in the galaxy that is warp and that has because of interaction. That
the plane.
Exactly.
Yeah. So two questions. So in terms of the face-on case, where the filaments keep being filaments, even downstream, there is the main shock, and then there are spurs, because what the gas that comes out of the spiral arm has a reverse shear in the arm for a while. It tends to unwrap a bit, and you can get secondary shocks. And those secondary shocks would give you new filaments. That is true. Generally, the ISM is moving so fast that any perturbation can lead to a shock, which can lead to filaments. So it tends to prefer a filamentary structure, it seems. In terms of the edge-on cases, an interaction will certainly wobble a disk, but with great effort, because the rest of the disk has a big perpendicular restoring force. It's the Z component of that planar force. And for a plane, the acceleration is rather constant. It's just by Gauss's law. So it's a large restoring force, even at perpendicular distance. And at the edge, there is a restoring force. So it's hard to flap a galaxy. But once you do, that with a shear tends to wrap up the flap. It can't get any cooler, and convert that regular flap into a thermal motion, which will make the disk a bit thicker. But it has trouble propagating inward. That I looked at this in the 90s. A perpendicular wrapping spiral will propagate that perpendicular forcing inward a bit and give you a perpendicular warp, which moves inward and then eventually heats the inward disk a little bit. But the restoring force is so large, and you're climbing up the exponential disk, that a large flap in the outer part is only a small flap in the inner part. It could lead to the shingles and other structures we do see in our galaxy and other galaxies, but they're small. So the main disk tends to stay pretty flat and thin. And the flapping that you see tends to be the outer part of the exponential, out R25 or greater, which is what the H1 people have been telling us all along. Now barely see it in stars. Vanderkert has been saying, there's an edge out there. It's really where it gets thick, and where the exponential, because it gets thick, the midplane density goes way down out there. That's where the Kennicott-Schmidt relation now has a slope of 2 because of the flare, and the density is dropping rapidly. All kinds of things happen in this outer flare. But the inner part is staying mostly regular and flat.
Thank you, Bruce.
Thank you. Angeles?
Yes, so hi, Bruce. Thank you very much for the talk. It was really nice also because I love spiral arms, so it was for me a pleasure to hear you again. So I have a question based on the nature of the spiral arms. I'm very curious if with this kind of substructure that we can observe, we can infer something about the spiral arms are transient or long-lasting. Could you say something about that?
Yeah, that's really good. That's really good. There's been sort of the lore is that the grand designs can be somewhat long-lasting.
Mm-hmm, exactly.
The caveat to that is that even C.C. Lin said that they were growing instabilities. There was always the growth term, the omega term. Mm-hmm. What he would plot is the eigenvector. It's the structural term. And they grow rather rapidly, essentially in epicyclic time. Or it's what's happening is that the epicycles are getting aligned. And that spiral, which is the alignment of epicycles, grows because more and more epicycles are getting aligned. The epicycles are perturbed by the gravity and they get aligned. So that grows, and it should grow in only a few rotations. And in addition, as you know, Toomre pointed out, the arms will wrap up. Mm-hmm. That's a second effect. Lin and Jim Mark replied later, okay, it wraps up, but then it bounces in the center and you got a leading arm coming out. And so now you have a standing wave, which we think is true. These are standing wave patterns. And the standing wave can last for a while. Okay, but maybe it's 5 rotations because it's still growing. Mm-hmm. It amplifies a co-rotation. So I've been thinking for a while, yes, it grows, but then it goes nonlinear. We know they're somewhat nonlinear anyway. And then it starts to break apart because it's so nonlinear. What we're seeing in these clumps and then the regularity of clumps along spiral arms, and then the inference that that little dust lane has to be all about the same age to get the regularity all now is yes, indeed, these are fairly young structures. The M51, you know, nice grand design, it's got that recent interaction. It's a young spiral. It's just now accumulating that dust lane and just now starting its collapse 30, 50 million years later from the accumulation. So my guess is that a lot of these dust lanes are quite young.
Great.
On the other hand, there could be a regularity that could have formed this regularity of 70, 80 million years ago at the last passage and just be building it up now again. But then what's building up now again is rather young. But I would say generally the smaller spiral arm pieces are probably quite young, less than 100 million, 50 million years maybe. The grand designs are on the order of 100 to a gig a year, 100 million years to a gig a year, always on the verge of destruction because they're going more and more nonlinear. The shells, of course, are young, and the dust lanes are probably younger than any of these.
Good. So, well, I was very curious about that because that means that maybe not all the spiral arms that we can observe in the galaxy, in the external galaxy, even in our galaxy, could follow the Lin and Xu theory.
Well, Lin and Xu cover everything. They just said it was a density wave and they had the equation of motion. Toomre said swing amplifier, but that is part of the standing wave. That's the amplifier for the standing wave. A perturbation will give you the wake, so you're trailing, that will wrap up. Toomre said that. Then Lin and Mark came back and said, okay, it wraps, but then it bounces, and it can bounce as a long wavelength trailing, or it can bounce as a short wavelength leading, which when it comes back to that initial perturbation, now the leading and the trailing meet at the same point, and now the swing amplifier converts one to the other with amplification. So the trailing comes in stronger, bounces again, comes back stronger, and that amplifies. So that's what grows the standing wave. When you just have a reflective boundary condition on the inner part, usually a standing wave has two reflective boundaries, a radiating condition in the outer part, but now you've got that amplifier in the middle. So the swing amplifier is part of the general Lin, Xu, Mark global mode theory. And now Selwood is talking about global modes as well. He never believed that before, but his models have modes just moving around from place to place. And in his modes, they degenerate also because they go nonlinear. It's entirely consistent with the original Lin Xu theory as modified in all these years.
Okay, thank you very much.
Thanks. Okay, questions? Okay, well, this is an excellent talk. Thanks, Bruce, for this. You can open your microphone or send reaction to give the same to Bruce.
Thanks a lot. Yes, wonderful.
Thank you.
Very nice to see you again,
My
Bruce.
pleasure. Great to see all of you. Great to see those of you from many years.
Yes.
Hope to see you again very soon.
Okay.
Thank you.
Drop in anytime. Drop in here.
Love to.
We're getting off this damn thing now, so you